Hello everybody, I'm Daniel and I'm going to talk about Meena towards a human-like chatbot. So how do you build a chatbot that can handle virtually any imaginable conversation, right? Well, there's sort of a precision first approach where you start with nothing and then slowly you build more and more components until you cover a large space of conversation possibilities. And then there's the recall first approach where you start with a general technique that doesn't quite work in the beginning and then you improve the technique and it gets better and better and better and better. Until eventually, hopefully, you'll cover the whole space of possibilities with high quality. And this is the approach we're taking for Meena. But let's take a quick step back first before we go into what is Meena. When I was a child, I built a chatbot, and it was a rule-based chatbot. I spent a lot of time on it, but no matter how much time I spent on it, I noticed that that chatbot would never reach human level. Because the technique was just not scalable. And as time went by, NLP and ML got better, but it was not clear if we had a scalable strategy that went beyond solving different pockets of problems. Then in 2015, I saw a paper called the Neuroconversational Model, and things changed for me. My hope that it was that we had found potentially scalable technique emerged, and as you can see here, the human and machine have reasonable high quality dialogue, especially for the time, and especially compared to rule-based chatbots of the time. And lo and behold, it was trained end-to-end on movie subtitles. Means none of this was engineered to work with these particular inputs. And as you can tell, it doesn't quite look like movie subtitles you would watch in a movie. Pointing to some very exciting generalization possibilities. So I founded and led a team at Google Brain to work on the Meena chatbot, and in 2020 we published this neuroconversational model that could, in some ways, even show early signs of what some people would call maybe creativity. So. In this conversation, you can see the user and Meena were talking about cows, and then Meena said, well, I heard they go to college. And then the user goes, oh, cows go to college? And Meena said, I heard a cow went to Harvard. And the user, what did the cow study? Meena says, bovine sciences. And then I think the user sort of tried to push her, see if she would say something that makes sense. Do horses ever go to Harvard? And Meena said, horses go to Havard. And the user acknowledged it was a pretty good joke. And Meena actually says you're trying to steer that swap, which some people think it's another reference to cows and horses, the word steer. So that was a pretty incredible response, in our opinion. Horses go to Havard. Because if you look at the training data, although it's very large, there's only one example in which the word Havard appears, and the word horses does not appear in the same utterance. It actually appears on the previous utterance. Both of these words are used in a completely different way, and in this entire conversation example in the training data, there's nothing about cows. So it was quite an interesting leap of generalization, I guess one could call. And you might ask, how do you train a chatbot that can come up with this type of, arguably creative stuff? Well, this is a classical objective. It just predicts the next word, even the previous ones. And in fact, people have been training neural language models with this exact goal of predicting the next word since the year 2000. This goal is also known as minimizing perplexity of the next word, minimizing cross entropy, autoregressive language model, causal language model, and so on and so forth. And of course, non-neural language models have been around for even longer. I think in this moment, there's opportunity to bring up the Jan LeCun's cake. So Jan LeCun once said, if machine learning is a cake, then unsupervised learning is the actual cake. Supervised learning is the icing on the cake, and RL is the cherry on the top. And we like to believe we're essentially working on the cake. And the reason is we have so much potential data. If every word was a label, then public internet text would arguably be humanity's largest label data set. that one could use for predicting the next word as an unsupervised training method. So leveraging this to an extent, Meena was trained on 341 gigabytes of text filtered from public domain social media conversations using an end-to-end 2.6 billion parameters model. So which is a sequence-to-sequence model, which is basically a language model. And instead of using the traditional transformer, he uses a evolved transformer, which is a neural architecture search variation of the transformer that provides better performance in our testing. So as you can see in this diagram, the higher level functioning of the model is very simple. In goes the entire conversation history as text concatenated together and then tokenized, of course. It gets encoded, decoded, and then out comes word by word the response, generated response, and is just it basically is just getting served the way it's trained. It's trained to predict the next word. So here is basically just using the predicted probability distribution, and then we just sample the next possible word. I'm going to talk a little bit more about how do we turn the probability distribution into actual decoded text in a way that we found to be optimal for us. Basically, this is a very common technique that a lot of people use, especially in machine translation, to generate responses given this probability distribution over the next possible word. And oh, by the way, when I say next word, predict next word, I really mean next token. In our case, it's a subword. Sometimes people even use characters, but I say it next word for simplicity. As you can see here, the input to the model in this case is why do you like the ocean? And then the model generates the following potential responses, right? These are alternatives. Why don't you like the ocean? I don't like the ocean. I love the ocean. I don't like the ocean. I love it. I don't like the ocean, comma, instead of period. I love the ocean, and so on and so forth. There's a lot of I don't likes. It's a little short, a little repetitive. It's a little nonsensical too. And sometimes gets contradictory. Maybe there's some examples in which it gets even more obviously contradictory. So that was not working very well for our case. Basically, we imagine the reason is, beam search is just giving you the mode, the most, likely possible response amongst the possible responses that you can cover with your beam search. And the mode, not too surprisingly, is going to give you something that most people would say as an answer to not just this question, but to anything, right? So saying you don't know or you don't like is a very form of response to like many things. So it's not that surprising that when you request the mode, the most likely possible sequence of words, you get things that are generic and a lot of I don't knows, I don't like, and so on and so forth. So what do? We do something that we named sample and rank, which is very simple. We just sample each word after the other, following its predicted probability distribution. So basically, instead of trying to get like the most likely sentence overall, we just randomly sample according to the predicted distribution the next word. So there's no attempt to optimize across the sequence of words. And the other thing we do as well is for each one of the words that we sample, we actually don't exactly sample according to the original probability distribution. We modulate it using a common technique called sampling with temperature, where we divide the value of the largest before the softmax by some temperature T. And basically that allows us to control how diverse but potentially nonsensible versus less diverse but potentially more bland the response we want. So these responses, I believe, were generated with temperature 0.88. And the closer you get to 0, the closer you get to basically doing just plain greedy decoding. But basically, as you can see, the question here is the same. The model we use to generate these is the same, but the responses look much more natural and interesting, right? Because we're not requesting the mode sequence of words, we're just sampling according to the learned distribution. And there's things like, I love the beach, I like that it doesn't have anything in it, just open water, it's dark and mysterious, the sea sounds cool, etc. And so this is the sample part of sample and rank. The rank part is that we take the probability scores according to the model of the entire sequence. We actually normalize these scores by dividing by the length, such that we, in order to not get really small scores for really long sequences, which would naturally occur otherwise. And then we just sort it, and we take just the top one. If you actually sample a certain reasonable number of response candidates, and then you just pick the top one according to this, just the length normalized score. In our experiments, we get much better results than doing either beam search or even just doing random sampling with just one sample, meaning just doing one candidate. All right, so going back to our diagram, basically the main pros of this approach is that you get to avoid having to build or train any sort of intermediary components, right? And at the same time, you can cover lots and lots of potential domains through the very vast amounts of data you train your unsupervised objective of just predicting the next word on. And as you can tell, there's no explicit intent classifier, no entity extractor, which means we didn't have to collect any specifically labeled label data for training these separate components. And there's also no explicit dialog manager or policies. Of course, all these things might be happening implicitly inside the model, but we didn't have to craft them separately and put them together. It's just all learned end-to-end from the input context text to the output context text. So these two pieces of data, the context history, the conversation history, and the conversation response are the only two pieces of data we need to train them on. But what's the downside of this approach, right? And currently it's basically, although it has all these incredible benefits, it cannot really do some basic things, namely say things that make sense all the time, and or say things that that are specific to what you're asking. So it's getting much better, and this is what I'm going to show you later. And there's like a path to make it better, but currently it's not quite there yet. It's not as consistent as, let's say, a person would be in making sense all the time, or being specific at least a reasonable amount of times. So at this point, it's extremely important to ask, is just getting better at predicting the next word enough to get to these basic contextual conversation abilities, like making sense and being specific? And in fact, this is the main point of this talk. So to answer this, we set up some crowdsourced evaluation of these basic human likeness attributes, such as making sense and being specific. And I'm going to describe now how we did this. So first, you start with like a multi-turn context. In this example, do you know how to swim? Chatbot says yes. Then what's your favorite stroke? And there's sort of two ways we use to create this. And the results kind of roughly agree between the two. The static evaluation, we just kind of build the context a priori. Like for instance, this one, we would write this before even giving it to the chatbot. And the interactive evaluation mode, in which the chatbot and the crowd worker interactively and together, they just have a conversation, and the context is a result of that. So then this context is given to the chatbot. Chatbot gives you a response, and then the crowd worker who's evaluating the response given this context will say, well, this response is sensible. This is a swimming stroke, butterfly stroke, and is very specific to this context. However, if the chatbot says, I don't know, crowd worker will say it's sensible but not specific, because you could literally say, I don't know, or no, almost literally to any sort of question. And if the chatbot says the one that shines, then it doesn't really make sense. So the crowd worker is likely to say it's not sensible. Then the fraction of responses that are sensible, we name it sensibleness. And likewise, the fraction of responses that are specific are named specificity. Then to summarize the results, we just take a simple average, which we call sensibleness specificity average, or SSA for short. Then, why do we care about having specificity in this metric, right? So here is like a simple case study where we basically pit a generic bot versus a general actual open domain bot like Dialog GPT. And you can see that generic bot basically just says, okay, and I don't know all the time. However, because these two statements can kind of fit with a lot of different contexts, the sensibleness we estimate with a smaller sample than usual for generic bot is like around 70%, but the specificity is 0, according to the crowd workers. And therefore, its SSA is really low, 35%, as it should be. But however, Dialog GPT, even though it shows us smaller sensibleness, its specificity is much more reasonable, and therefore its SSA is higher, as it should be, 51%. Now, here's an actual concrete example of 2 responses from this generic bot and Dialog GPT. And to be clear, generic bot is like a construct of ours that just says, okay, and I don't know, that we created for the purpose of illustrating the importance of specificity. So let's say the input is, you know nothing, Jon Snow, right? Generic bot will say, okay. And Dialog GPT will say, the North remembers, which is sort of like a reference to the show. Which is specific. Now, it turns out that getting better at predicting the next word is correlated with basic contextual conversation, which is, again, responding to that main question, and this is the main point of this talk. So basically here on the vertical axis, we see the SSA, which is the metric I just described, computed by, measured by labels from crowd workers. And here on the x-axis, there's the performance of the model at predicting the next word. So this is an automatic metric that basically measures how good the model is at predicting the next word, and the smaller the better. And in fact, if the perplexity is 1, theoretically the model can predict exactly what is the next word given the previous ones, right? Which, may or may not be reasonable depending on how much context input, previous words or that the chatbot would have to make that prediction. Sometimes there's just multiple potentially equally correct next words. But yeah, the theoretical minimum is just 1. And you can see here that, surprisingly to us, the perplexity not only correlates with SSA, which are these basic contextual conversation abilities, but it correlates linearly. And there's the possibility, and this we estimated the human level here, SSA, for sort of a random cohort of human crowd workers, and improve the model's ability to predict the next word. There's a chance that we might reach human level, and that's a huge deal for us because it's sort of the answer to, is there some sort of scalable way, a potential way to get closer to reaching human level. So in conclusion, neural language models like Meena are a promising way to create chatbots that can handle a multi-turn conversation in an open domain setting. And things are sort of just starting to work better, and hopefully further next word prediction optimization can lead to more interesting results. Thank you very much, and here's my contact.